So let's just start with the proof of the theorem. So in the first part of the theorem, we have to show that if you have d eigenpairs in which the eigenvalues are distinct, then corresponding eigenvectors must be linearly independent. So in order to show that these d vectors are linearly independent, we need to make one linear combination of it, okay, and assume that their linear combination is equal to 0. And we would like to show that all these constants are 0. In other words, you can't write any one of the vector as a non-zero linear combination in the terms of other vectors actually. Okay, so this is what that we would like to show. Now, if lambda 1, lambda 2, lambda d, these are the d eigen values of the matrix A. So these are some distinct number, could be real number, could be complex numbers. I hope we all know what we mean by the Lagrange interpolation formula. So the Lagrange interpolation formula is kind of a trick actually. So it's a method, okay, through which you can take, for example, some numbers, okay, so you can take say 10 numbers and you can construct an explicit polynomial or some polynomials whose root are those 10 numbers actually. Okay, so for a given set of numbers you can always construct a polynomial whose roots are that number. Okay, so I'm assuming that everyone knows the Lagrange interpolation formula. I mean, if not, you can tell me in the Zoom session, we can have a discussion on it actually. Okay. Now, by Lagrange interpolation formula, we can find d polynomials. There are, say, d polynomials such that pi, so if you take the ith polynomial and say substitute jth eigenvalue in it, you're gonna get delta ij. In other words, you're gonna get 1 if I is j, in other words, and you're gonna get 0 if I is different from j. In other words, these d polynomials are the kind of polynomial in which, so in P1, if you substitute lambda 1, then P1 of lambda 1 is equal to 1 actually. And if you substitute lambda 2 or lambda 3 or lambda d into the P1, you're going to get 0. Okay? In other words, using lambda 1, lambda 2 to lambda d and interpolation formula, we constructed a polynomial P1 such that lambda 2 to lambda d are the roots of P1. Okay? And what is P2? So the P2 is a polynomial whose roots are lambda 1, lambda 3 up to lambda d. Okay? Not lambda 2, because when the lambda 2 is substituted into the P2, you get 1 actually. Okay? So in this manner these polynomials has been constructed. Now using such polynomials we're going to show that in this combination these constants are 0. Okay? These constants are 0. And how can I show that? Simple. So if I take, for example, ith such polynomial and substitute matrix A into it, and I operate or multiply it with Ci, Xi, with this linear combination Cv, Xd. I know this is equal to 0, so the Pi of A multiplied with 0 will give you 0. Okay? And 0 equal to Pi of A multiplied with C1, okay, C1 x1 plus so on and so forth, pi of a, say, operated onto ci xi plus so on and so forth, and pi of a operated onto, say, cd xd equal to all of this equal to 0 actually. Now what are you going to get? So C1 is like constant, you can pull it out, and the pi of a operated onto x1. So you're going to get what? I'm going to get pi of lambda 1, okay? Pi of lambda 1, why? Because I know that p of a operated onto x gives you lambda x if the lambda x is in p of lambda x if the lambda x is an eigenvector actually, eigenpair. So we proved it in the beginning. This identity we proved it. So using this identity, pi operated onto multiplied with x1 will give you pi lambda 1 x1, okay, and plus so on and so forth, plus ci and pi lambda I operated onto xi plus so on and so forth, cd pi operated onto lambda d, because pi of pi evaluated at a multiplied with xi would give you pi evaluated at lambda d multiplied with xd, and all this is equal to 0. Now with this definition, if these two indices are different, then you are getting 0. So this term will go away, all terms will go away except, you know, this term. But pi of lambda I is what? Pi of lambda I is equal to 1. So this means the only terms that will survive is ci xi equal to 0. Okay? Now, xi is eigenvector. So xi can't be 0. So this means that ci must be 0. So what does this calculation show? So if I take the ith polynomial evaluated at a and operate it on the given linear combination, I'm getting the conclusion that ci is 0. So if I just take I equal to 1 and do this calculation, I'm going to get c1 equal to 0. If I take I equal to 2 and repeat these calculations, I'm going to get c2 equal to 0. In this manner, I can show that all of these ci's are 0, and hence this shows that the vector x1, x2, xd are linearly independent actually. Okay, they are linearly independent. So let's do the second part. Second part is really the corollary of the first part actually. It's really the corollary of the first part. That Y matrix A has at most n eigenvalues. Okay? Y at most A has eigenvalues. So suppose there are, by the way, what is the dimension of Fn? In other words, Cn or Rn. So it's a Rn or Cn. So its dimension is equal to n actually. So in this Fn, if you take more than n vectors, they must be linearly independent. They must be linearly dependent actually. Okay? They must be linearly dependent. And if you have, in other words, in this vector space, the number of linearly independent vectors that you can have together are n actually, at most n. In other words, you can have 2 linearly independent eigenvectors, you can have 3 linearly independent vectors, you can have 10 linearly independent vectors in Fn, You can have n linearly independent vectors in Fn, but you can't have n plus 1 linearly independent vectors in Fn actually. So if you have some number of linearly independent vectors, okay, if you have some number of linearly independent vectors, that number must be less than or equal to n. It can't be bigger than n. Okay. Now let x1 up to lambda d xd are distinct eigenpairs, okay, of matrix A. Okay, the distinct eigenpairs of matrix A. They are distinct eigenpairs of matrix A, in which each one of these vectors x1, x2, xn are elements in Fn. Okay, these vectors are elements in Fn. Now, if lambda 1, lambda 2, lambda d are distinct, as we have in this theorem, so this theorem tells us that these vectors, so this x1, x2, xd, they are linearly independent in Fn. They are linearly independent in Fn. Now tell me, what could be this d in other words, what could be the number of vectors that are linearly independent in Fn? So this d must be less than or equal to n. In other words, you can have two linearly independent vectors in Fn, 3 up to n, but you can't have n plus 1 linearly independent vectors in Fn. So this d must be less than or equal to n actually. And d is also what? D is the number of distinct eigenvalues that a matrix can have. So this really shows, hence, this really shows that A has at most n distinct eigenvalues. Okay? A has at most n distinct eigenvalues. They can't be more than n distinct eigenvalues for the matrix A. And this is really obvious actually. Okay, so this part is really obvious. If A has exactly n eigenvalues, that means there are exactly n linearly independent eigenvectors. So if you have, so since the dimension of this space is n, so any n linearly independent vectors would constitute a basis of Fn actually. So this really completes the proof of the theorem actually. Okay, this really proves the theorem. Okay, and what does this second result shows? This theorem shows actually that there are at most n eigenvalues of a given matrix A of order n by n. You can't have more than n eigenvalues for a given matrix of A n by n of order n by n. Okay, so we saw previously it was n square, but now you have a sharper bound on the number of eigenvalues that they can be at most n actually. It can't be more than that actually. Okay, and if you have n eigenvalues, then they constitute a basis for Fn. So this is an important fact that we're going to use later at different places. Okay. Let me define now define something which is called the Eigen Space associated with lambda. So here's the definition. Next, let lambda be in the spectrum of matrix A, in other words, it's an eigenvalue of the matrix A. Okay. Then the null space, null of A minus lambda I, this matrix, A minus lambda I. In other words, from the matrix A, from the diagonal entries, subtract lambda for the matrix and consider the null of it. For the null space of A, minus lambda I, okay, the null space of A minus lambda I is really called the Eigen Space. Okay, this is called the Eigen Space of the eigenvalue lambda. So this is the Eigen Space of A associated with lambda. Let me define the eigenspace next. Eigenspace of matrix A associated with lambda, okay, with the eigenvalue lambda. We're going to denote this by eigenspace, this calligraphic E of A, E lambda of A, okay, E lambda of A. And by E lambda of A, I mean the null space of the matrix A minus lambda I, okay. And what would be basically the null space of the matrix A minus lambda I? So the collection of the vectors X, okay, obviously from Fn, such that when A minus lambda I operates onto X, it gives 0. And what do you mean by that? X belongs to Fn. Okay? So this is going to be Ax minus lambda x equal to 0, or I can say Ax is equal to lambda x actually. So what is the eigenspace of the matrix A? So the eigenspace of the matrix A, if you write it explicitly, I can say that it's a null space of A minus lambda I, but explicitly it's the collection of the all eigenvectors, or the all vectors that satisfy this equation, Ax equal to lambda x actually. In other words, it's the collection of the all eigenvectors corresponding to the eigenvalue lambda. Okay? It's the collection of the all eigenvectors, subspace of the all eigenvectors corresponding to the eigenvalue lambda actually. So in fact we can prove that, okay, I'm not proving it, you can check it for yourself, that this E lambda of A is a subspace. Okay? So it's a subspace of Fn actually. Okay? The collection of all eigenvectors corresponding to the vector lambda. Let me define another thing. That is the dimension of the eigenspace of matrix A associated with the lambda. So the dimension of the eigenspace of lambda, okay, we call it, okay, we define it to be that this is the geometric multiplicity. Okay, it's the geometric multiplicity of eigenvalue lambda. Okay, So what do we mean by the geometric multiplicity of an eigenvalue? It's the dimension of its corresponding eigenspace. Here is a little remark. Okay, little remark. The remark goes like this. So if lambda is not an eigenvalue of the matrix A, so if lambda is not an eigenvalue of the matrix A, then Ax equal to lambda x is not satisfied actually for any non-zero vector x actually. Okay? Ax equal to lambda x is not going to be satisfied for any non-zero vectors x. Why? Because if Ax is equal to lambda x, then it will become a lambda, eigenvalue actually. So if lambda is not eigenvalue, that means that Ax should not be equal to lambda x. Then I can say Ax does not equal to lambda x for all non-zero x. The only x which is going to satisfy this condition is going to be x equal to 0. In other words, then this E lambda of A is going to be 0. Okay? It's going to be 0. So, what would be then the geometric multiplicity of the lambda? Okay? What would be the geometric multiplicity of the lambda? So, since its eigenspace is 0, so the geometric multiplicity of the lambda must be 0. So, hence geometric multiplicity of lambda is 0. Okay? It's 0. Lambda is indeed in the spectrum of the matrix A. In other words, it's an eigenvalue of the matrix A. What could be the dimension of the eigenspace of the matrix A associated with the lambda? So it's going to be a number D. It's going to be a number D. But this D is going to be something between 1 and n actually. So it could be 1, okay, and it could be what do you call at most n actually, okay, because this is a dimension, this is a subspace of Fn. So if it is a subspace, its dimension can be 1 and it can be at most n. Okay? Since lambda is eigenvalue, so it can't be 0 actually, because there are going to be some vectors for which this is true. So this is not going to be a trivial set actually. Okay? Eigenspace is not going to be a trivial set. So if lambda is indeed an eigenvalue, okay, then the dimension of the matrix A is going to be something between 1 and n, and hence we're going to say the geometric multiplicity of lambda is going to be something between 1 and n actually. So if you want to have an explicit formula for what is going to be the geometric multiplicity of lambda, okay, let's denote this geometric multiplicity by G lambda. Okay, for this I'm gonna use a symbol, say G lambda. So G lambda is the geometric multiplicity of the lambda. It's equal to the dimension of eigenspace of A. Let's use the rank nullity theorem. By rank nullity theorem, the dimension null space of A minus lambda I matrix plus the dimension of the column space of A minus lambda I, it must be equal to n. It must be equal to the dimension of the entire space lambda n actually. Okay? So the dimension of a null of a matrix and dimension of a kernel space of that matrix, this sum should be equal to n actually. So this means that the geometric multiplicity, and by the way, what is the kernel space of the matrix A minus lambda I? The kernel space of A minus matrix lambda I is really the rank of the matrix A minus lambda I. Okay? It's the rank of the A matrix A minus lambda I. So therefore, dimension of null of A minus I, this is G lambda, okay? This is G lambda is equal to n, okay, the dimension of the entire vector space Fn minus the rank of the matrix A minus lambda I actually. Okay, so the geometric multiplicity is not difficult to find. You just find the rank of the matrix A minus lambda I, subtract it from the dimension of the vector space that you are in, you're going to get the geometric multiplicity of the eigenvalue lambda actually.